for the Fort Hood Fundamentals of Engineering exam review. Next we're going to do something I don't see that much of, but it's in the book. Therefore we wouldn't take a chance on having it show up on a quiz and us not know how to do it. It's too easy. It's a turnbuckle, or a power screw they may call it, a jack, a mechanical jack, anything that has square threads on it. The equation is listed in your review manual. It says M, that's the moment necessary to crank this rascal up, is equal to P, that's the load that's applied, multiplied times the radius of the screw. In this case we're given the diameter is 10, so the radius will be half of that, multiplied times the tangent of an angle alpha plus an angle phi. Both are defined. Actually that's plus or minus, because if you screw the thing against the load and raise a load, you use the plus. How much moment it takes to loosen it and let the load fall would be minus, because the friction acts in the opposite direction. In our case, the coefficient of friction in the device is 0.25. It is a 10 millimeter diameter rod. The pitch of the threads is 2 millimeters. That's the distance between any two threads. So for us, the load P would equal to 2 kilonewtons. And actually we're not just raising it up against one. We don't have just the friction inside of one of these. Since it's a turnbuckle, you have another one on the other end of the turnbuckle. So we'll multiply the load times 2, make the load 4. The radius, since our diameter is 10, the radius is 5 millimeters. The angle alpha is defined in the book on page 20 as the pitch angle of the thread. Now the pitch angle of the thread, these things go around and they go up in the air like that, and how much they go up versus how far they had to go to do it is what they call the pitch angle. So in this case, this dimension is 2 millimeters, and it went around the thread. The distance around the thread is 2 pi times the radius, or pi d. So this angle is how far it went up, 2 millimeters up in the air, divided by it had to go around this slope to get there, 2 pi times the radius. The radius is 5 millimeters. That's what they call this pitch angle. And then finally we have this angle, which in the book is defined as the arc tan of the coefficient of friction. So in other words, to get the angle to be added in this equation in degrees or radians, whatever you're going to use, you take the angle whose tangent is the coefficient of friction. In our case, phi is the arc tan of 0.25. That's the specified coefficient of friction. And that angle is equal to, we went ahead and worked it out, 14 degrees. Alpha, if you just take 2 divided by 2 divided by 5 divided by pi, it turns out to be 0.064, but that's in radians. You'll notice millimeters over millimeters has no units, so you got to multiply that times 180 degrees for every pi radians, and that comes out 3.64 degrees. And from then on, it's nothing but a matter of just putting it in the equation. The moment is equal to the load is 4 kilonewtons multiplied times the radius is 5 millimeters multiplied times the tangent of the angle 14 plus 3.64. You multiply all that out and you get 6360 Newton millimeters. A little unusual term there. It would usually be Newton meters, so probably the book would say 6.36 Newton meters. Alright, now then, they throw a few tricks at you, or they may. This is looks like a relatively simple problem. Got a box, uniform density, total load 600 newtons. So in the middle of the box we could put 600 newtons of load. Suspended by 3 equal length cables as shown. Point E is directly above the box, and that is a half a meter above the box. And you really need to watch out for things like this. It's not that they're trying to trick you, they're just trying to make sure you really understand what's going on. If this force right here had any value at all, summing moments about this line wouldn't be zero. In other words, if you sum moments through a line across or through CB, this force has no moment arm, this force has no moment arm, this force has no moment arm, and so if we put something in here, his vertical component will tip the box over and everything inside will fall out. So he figures you're probably going to realize that force is zero. The next thing is, you're so happy to get one of the numbers, you say, well, there's 2 wires, and therefore the answer must be 300. And you can be sure 300 is one of the choices. But what you got to remember is these forces are not straight up. Only their components are 300. The vertical component is 300, and the vertical component is 300. You'll have to find this angle right here. Knowing how far it is from here to here, that's half of the diagonal length. You can find the diagonal by taking this squared plus this squared, take a square root. That's half the diagonal length, and then a half a meter above the middle. Those 2 numbers right there would give you the angle of this wire, CE. Then you'd multiply the CE times the cosine of that theta and put 300 in each of the wires, and then you got the answer for CE. So watch out for things that look too easy. Alright, now we're going to get into larger structures than just boxes and knots on a string. So we need to know how they're supported. Typically they'll show you a roller. They may show you a nicer roller, but they both pretty much have the same idea. This device always causes a force, or there is available a force, perpendicular to the floor upon which the roller runs. If you see a roller looking like that, then the force looks like that. If this is 60 degrees, then this is guaranteed to be 30 degrees. Is that right? Yeah, because it's 90 degrees away. So even if it's an angle, you ought to be able to tell that's not any longer an unknown. That is a known direction for that force. Sometimes they show them like this. They'll just show them sliding and tell you it's frictionless. Sometimes they show them as a little rocker. A cable forces always run right down the axis, and if he says it's a cable, you can probably be pretty sure it is a member that is in tension, so you would show the reaction on the member as a pulling force. This would do the same thing. The only difference is this one would take tension or compression. When you put this arrowhead on the member, you're pretty sure its direction is correct. When you put this arrowhead on the free body here, then you do not know if the direction is correct. The arrowhead might ought to push instead of pull on that joint. That's this one. Here's a frictionless guide. It causes vertical reactions only, because if it tried to cause a horizontal load, the collar would just slide, or this piece would just slide inside of this hole. Here's a built-in fixed support. In general, if you push down on these things, they'll resist. If you pull on them, they will resist. If you bend them, they will resist. So a built-in fixed support has the possibility of 3 support reactions, all of which would be unknown. All of these arrowheads would not be guaranteed to act in that direction. You'll have to guess an arrowhead, and then when you solve for it, if this arrowhead comes out minus, it means the arrowhead properly belonged on the other end. Then a pin, all pins have the ability to resist on this member with 2 forces, a horizontal and a vertical force. Again, these arrowheads may prove to be incorrectly shown and guessed when you start off. Here, this author shows like a pin on a real rough surface, but I'm sure the quiz would never do that, because that looks too much like that one we showed earlier, like this one here. You'd never know the difference between those two, so you can pretty well forget that possibility on the quiz. Alright, now, in order to find out what these supports do on a given structure, if you see a pin has the possibility of resisting with a vertical force, and so you would say RA vertical would be a relatively good name for that guy, and RA horizontal because it's a pin. Here you see a roller. It's got 3 little wheels on it. The only force possible for that one is a single vertical force. I'm guessing these forces are probably up, but that doesn't guarantee it. Sometimes the forces may be mixed up in direction all over the place, and you don't know which way they go. A good name for him, since he's at joint C, is the reaction at C vertical. Now this is your free body. The reason I showed you these reactions is because I cut through the soil, I cut through the support. When I cut through the support, I must show the reaction that that support used to cause on the free body. Now, to solve for those forces, we would sum moments. I would suggest about point A. The reason I suggest we sum moments about point A is because 2 unknowns go through that point, and that will cancel both of those unknowns. So it would read sum moments. Let me get another piece of paper. Let's leave that where we can see it. Alright, we're going to sum moments about A equals 0 is equal to, we'll take this 3,000 Newton force, let's just call it a 3 kilonewton force and work in kilonewtons and save some zeros, times this dimension right here. You'll notice this 3,000 Newton force is perpendicular to this member, and therefore it can't get any closer to the point A than the length of this member. So if you take 5 squared, since this is 7.5, this one right here will be half of 7.5. because of similar triangles. So you take 7.5 squared over 2. To that you add 5 squared, and then hit the square root button and you get
6.25.
6.25, so there's his moment arm. 6.25. To that you add 3 kilonewtons up there at the top times 12.5, since he's twice as far up, plus 3 kilonewtons times 5, that's this one here, plus 3 kilonewtons times 15, that's this one over here. Looks like all of them. Has this one here, of course, but he goes through point A, so we don't have to mess with him. Minus the reaction at C vertical, and multiply that times 10 meters, and solve for R sub CV, whatever it is. Doesn't really matter. Did you already get it?
11.6.
Okay, 11.6 kilonewtons. You have to be a little careful because everything else is shown as newtons. Then you get sum forces vertical and get this one. Now, getting the sum force horizontal, you're going to have to break these rascals down into components anyway. So that means you're going to have to find this angle, and that's easy now. Who has an angle 7.5 over 2 divided by 5? That's opposite over adjacent. How many degrees?
36.9.
So that's 36.9 degrees. So what that means is this is 36.9 degrees in there, and this is 90, so what is 90 minus 36.9?
53.1.
53.1 degrees in there. So here again, we will find the horizontal component of this one by 3 kilonewtons times the cosine of 53.1. There'll be another one here. Don't forget this one here. This one counts. There'll be 3 of those. Those are the only people pushing to the right. This guy will equal to 3 times cosine of 53.1 times 3 of them. What'd you get for that?
5.4.
5.4 kilonewtons. So finding the reaction should be pretty easy. It's basically sum of the forces about some point, setting that equal to 0, summing the forces in the x direction, setting that equal to 0, summing forces in the y direction, and setting them all equal to 0. Since you know how to do components, you can do these, and since we've been talking about how to do moments, you should be able to do this one. Now, I notice on the question on this particular one that we got out of the book, it says all it wants to know is the force in member BC. Well, generally speaking, you cannot come in here and just cut a joint out and get much out of it. I mean, you're welcome to cut this joint out. You're welcome to show the forces now exposed because you cut that free body. You're welcome to give this force a name, FD, since it goes from F to D. You're welcome to give this force a name, FC. You're welcome to give this force a name, FE, and that's a good free body, and it's a valid free body. But since there's 3 unknowns coming into that point, you're not likely to get an answer. The reason is, the most powerful equation you've got, sum of the moments about any point equals 0. The reason that's such a powerful equation is because you can pick your point so that a lot of the forces go through that point and have no moment arm. That wipes a bunch of them out. Well, that equation doesn't work because all we got is point F. We don't have any moment arms anywhere. So you're left only with the sum of the forces in the X and the sum of the forces in the Y. And generally speaking, if you have 3 unknowns, you can't solve for those unknowns only having 2 equations. That's generally true. This is a little bit of a special case that you need to watch for. In this case, when I cut out joint B and properly show the force, properly show what I think the force is doing, properly show what I think the force is doing, put names on them. You really need names on them. This guy's name is BC. This is the force in BE. This is the force in BA or AB. In this case, the sum of the forces in the y direction does give you an answer. And the reason is because these two here are collinear. They act along the same line. They have no up and down component, and therefore this is the only guy that has any up and down component. He's this guy's only hope. So you say sum forces y equal 0 equals plus the force in member BE minus the 3 kilonewton force. Solve for BE. Ooh. Oh, is there... Alright.
Looking for BC.
I'm looking for BC. Thank you. I thought I was looking for BE. Well, I did a nice job of solving for BE. He just didn't ask for BE. He asked for BC. Alright. I'm glad you noticed that. My admonition remains the same. If you want to solve for a force like this that is perpendicular to two members, that's a very nifty little question to ask. It takes no time to solve. The answer is immediately apparent. BC is 3,000 newtons. BE, excuse me. Where is BC? Well, I'm not getting BC out of this thing. No way. So I'll have to do other work to get BC. All right, here's how you can get member BC. If you remember, when you had appendicitis, the doctor said, I think you got appendicitis. I'll tell you when he knew you had appendicitis, when he cut you open. When he looked in there and he saw what was going on inside, he says, it is appendicitis. Well, that's how you're going to have to find the force in member BC. If he asks you for BC, you're going to have to cut it. If you don't cut it, you won't be able to see the force inside there. Now you could cut round here and around here and around there and around there and around there and back around there if you want to. But every new member you cut adds one unknown to the problem and increases your grief proportionally. Cut as few members as you can. I see I can cut 3 members, and then I can come on around either end of the structure that you want to. You can come around this end or you can come around the other end. It doesn't matter. That's what you use for your free body. Every time you cut a member, you must guess which way that arrowhead goes. You need to remember also that this part of the free body is gone. I don't care if they have a force shown acting right through this stuff. I don't care if there's a 3,000 pound force perhaps right here, looks like it's coming through your free body. I don't care if he shows you a 3,000 pound force like that. That's not there. Nothing but what's inside that cloud counts. Alright, next, here is a guessed arrowhead. It may be wrong. Here is a guessed arrowhead. It may be wrong. This guy's name is BC. This guy's name is EC. And this guy's name is EF. Now then, it will be your job to put this little piece of steel in equilibrium by using the equations. Sum moments about any point, sum forces X, sum forces Y, all equals 0. Now here's the easy way to do that. There are 3 unknowns hanging out of that free body. It obviously is not going to just give up easy. You're going to have to do some work. But the easiest way is to ask, who are you looking for? You're looking for BC. So if you're looking for BC, cover it up so it doesn't show. Now then, who is left? Who do you really wish wasn't there? Well, I see EF and EC. Those two forces are causing me problems. If they weren't there, I would pretty easily be able to pick off this answer for BC. What you do is you follow these two forces until they meet at a point. You follow them until they meet at a point. If you'll sum moments about that point, they'll drop out because they won't have a moment arm. Therefore, the easy way to get the force in member BC is to sum moments about point E is equal to 0 is equal to. Now we have to go back and put our forces back on here because that's inside the free body. 5.4. Have to go back and put this force back on the free body. We never solved for that one. We're going to have to get this, we're going to have to solve for that one. Tell you another way. I'm not going to go ahead and do it. Let me just put F, because I know we can do it. All we got to do is sum forces vertical on the other free body. We'll just call it F to make sure we know how to do this. Here's your sum of moments about point E. First, this guy, no moment. Second, this guy, no moment. Third, this guy. 3,000 newtons times his moment arm, that was 6.25. And he gets a positive tendency to roll. Minus the force F, which we're going to have to get from the previous free body. Here's his moment arm right here, 5 meters. Then here's a 5.4 guy. He's 5.4 kilonewtons. And his moment arm is this thing right here. That was half of 7.5. We figured that out a minute ago. So that's 7.5 over 2 meters. And the sum of all that right there should equal to 0. And all you got to do then is solve for, oops, I don't have the cut force, BC, I forgot him. Let me add that cut force. That is a plus BC times his moment arm, that's also 7.5 over 2, equals to 0. One equation, one unknown. Very fast. Some of you using method of joints, we'll show you in a minute. I guess we already did, really. Back when they had that cable with the weight on it. You might go here and use method of joints to find this and this. Then you go here to find this and this by method of joints. And then you finally work up here. When you do that, you take a tremendous chance of making a mistake along the way. This is immediate, direct, instant gratification. These guys are gone. This is the only unknown. That's called method of sections. Alright. Now, let's solve for, I'm not going to actually solve for it, but let's start to solve for the force in member EF. Actually, our previous free body would work. I'm going to draw another free body. I'm going to draw a free body like this instead. The reason is I already know this force. I wish I hadn't drawn the free body around the left end. I never solved for that force, and the quiz never asked me for it, so heck with it. That force was 11.6 kilonewtons. Now I've got to redo my cut arrowheads. If you remember a minute ago, I guessed that the arrowhead for EF was a tension pulling on the joint. The only way something can pull on the joint is if it's in tension. A tension arrowhead. Now I don't know if I would have found out that was true or not, but if you do, you must show that arrowhead as a pulling arrowhead on the other end too. In other words, the only way this piece of wire right here can be in tension and pull on E is if you tie it to this other end and let it pull on F. So anytime you think that arrowhead points this way down this axis, that has to be shown that way.